be any axis system through the center of mass, but we have to be through the center of mass, because that's what the mechanics system says. And these moments in body axes have symbols, script LMN. I use that symbol so that you don't confuse them with something else. And a moment is, if you probably remember from mechanics, is R cross F. So R cross F is going to give you R cross F. It's going to give you a vector coming out of the board, yeah? Right? This is R and that's F, R cross F, and R cross F magnitude is the magnitude of R times the magnitude of F times the sine of the angle between them, right? So the sine of that angle is going to give you the perpendicular part of F. So R cross F, if there's no angle lambda between them, then you're not going to get any torque. And if the lambda is 90 degrees, you'll get maximum torque for a given force. And that torque vector is going to be coming out of the board. MV. So when you take the R cross MV in a similar way to R cross F, you get script L, M, and N. So what I expect you to remember from this, what matrix would go here? I would expect you to be able to do that. Okay. The cross product, flip on the other side, Ry and Rx. We add up all the pieces of mass. We break it up into little pieces of masses. And then we take the R cross MV of all the pieces of mass. All of them. This has to be the mass center. We use that little center system right there. That's called the center of mass or the center of gravity, CM or CG. And the diagonal terms of my angular momentum matrix, we call the moment of inertia matrix, are going to be looking down the I-axis, and that gives me y and z squared. Looking down the j-axis, that gives me x and z squared. And finally, looking down the z-axis like so, and that gives me x and y squared. And you see that this can never be negative, any one of those terms. Now, matrix math will tell you that because of that, because this can never be negative, this is called a positive definite matrix. Now, what does that mean for us? Well, it'll mean more later on this week for your readiness check. Basically, it means that the eigenvalues of that matrix are always positive, and the eigenvectors for that matrix are always real. Well, what's going to be here? Well, this is going to be minus the summation of all the MJs. So again, these guys are equal, these guys are equal, and these guys are equal. All the skew symmetric terms that we've been talking about before, those terms now are equal instead of being the opposite of each other. Now that there is your moment of inertia matrix. So it would be nice if we said that matrix, J, CM, B, that matrix JCMB times PQR in body axis. And we can see that the J terms are equal to the negative of these terms off the diagonal. So here's a secret handshake for arrows. If you go back in your mechanics book, they're going to give you an I matrix for this, and they're going to have plus signs over here. They're going to have plus signs over there. So what happens is this guy is going to turn out to be equal to, this term over here is going to be minus J, X, Z, and B. Do you see that? It drives me crazy, but this is the way. The moment of inertia matrix for aircraft, in other words, the J matrix is defined with all positive numbers in here, so you put the minus of the J term in the off-diagonal terms. It's convention. I didn't do it, so don't blame me for it, but if you look in your books, you'll see that's pretty much how they. So the moment of inertia matrix, if you look at the Y, Z, you're going to get 0 for the mass symmetry. If you look at the X, Y, you're going to get 0 because of the symmetry. So all the off-diagonal terms for an airplane will be close to 0 except for xz, where you have no match for the tail and no match for the engine on the other side. And the maximum moments of inertia looking either this way or this way. And the only xz term is going to be the one looking of HCMB plus, and I would expect you to be able to complete that line. Can you do it? Moments dB dt plus omega bi cross the vector, right? So omega cross is skew symmetric omega bi. I would expect you to be able to complete this now. Well, I'll get you started. So let's say this is going to be di dt of our moment of inertia matrix. So let's do this one term at a time. If I'm taking the derivative of this term and I'm in body axes, I can replace it with the pure derivative. Going back to vector mechanics is Rx times I dot plus Ry times J dot plus Rz times K dot. Go back to vector mechanics as you learned it. What happens to this if I'm in body coordinates? If I'm in body coordinates, then what happens to this? If I'm in body coordinates, I have no I dot, J dot, K dot, because I'm in those coordinates. So dB dt of R comma B only equals, there is no I dot, J dot, K dot in B because I'm in the body coordinates. Okay, just nailing that down one more time, if that's what you're taking your reference with respect to. All right, so let's review. So what is dB dt of HCMB times the derivative of this? There's no way to change the moment of inertia matrix, or it's negligible usually. It would only occur with fuel burning. So what would the derivative be of P, Q, and R in body coordinates? Again, I'm going slow because I would expect you to know this answer. If I'm taking the derivative of P, Q, and R in body coordinates with respect to the B frame, what is the answer going to be? P dot, Q dot, R dot, right? It's the pure derivative. P dot, Q dot, and R dot. Because I'm dB dt and the H is in the body coordinates. What is cap omega bi? Well, it's skew symmetric. It's minus the z component, R, the y component, Q, and minus the x component, P, and then the negatives across the diagonal, like so, and then again times H, which is J, CMB, and P, Q, and R. So we're almost done. All you got to do now is put JCMB in there. So we know that JCMB is going to be on body axes, JXX in body. I'm only going to have the off diagonal minus JXZ term in body coordinates, minus JXZ in body coordinates. The rest of the terms are all going to be 0. That's J. I'll let you multiply that out. When you multiply that out, LMN, you can go to Nelson and compare that equation with what he's got in chapter 3 in the reading assignment for this week.